Wildlife research has always been limited by what humans can see, when they can see it, and how long they can stay in the field. Animals don't behave on our schedule. Whales dive for nearly an hour, surfacing unpredictably in vast, open oceans, making close-range behavioral observation rare but essential for understanding their communication and social dynamics. Birds migrate thousands of kilometers across countries and continents, often facing threats from habitat loss, pollution, and changing climates. Insects fly in split-second bursts, yet their pollination behavior is critical to entire ecosystems and agricultural productivity, which are now under pressure from declining populations. Observing any of this consistently and accurately is a constant logistical challenge. Traditional methods, binoculars, GPS tags, motion cameras, can't keep up with the complexity, speed, or scale of real-world animal behavior. Now, researchers are turning to AI-powered robots to help watch and monitor wild animals. The goal is simple: to extend the reach of the human scientist's hands, eyes, and legs. Robots can go where people can't: deep underwater, inside dense hives, or across wide and remote landscapes. They can stay in the field for long periods without rest. They don't tire, they don't blink, and they can observe with precision for hours, days, even months. With the help of AI, they can also interpret what they see in real time, tracking, identifying, and analyzing behavior that would otherwise be missed. Traditional tracking tools are often slow, limited in resolution, and sometimes invasive. Satellite tags on whales, for instance, can reveal their general locations but miss the exact moment they surface, moments that are critical for visual observation and behavioral studies. Monitoring bird movement has traditionally relied on GPS loggers that store data on board, requiring researchers to recapture the birds to retrieve information. This not only adds stress to the animals, but also limits how many birds can be tracked and how frequently data can be collected. Video cameras can capture insect activity, but often with motion blur and without the ability to continuously follow individual movements or interactions. In the case of honeybees, manual hive inspections are disruptive and offer only brief glimpses into colony life, missing the complex, long-term dynamics of behavior, reproduction, and social interaction. These gaps in precision, coverage, and continuity are exactly where robotic systems are beginning to make a difference. Today's research robots are intelligent. Some use reinforcement learning to guide marine drones toward elusive whales based on real-time signals. Others rely on vision-based feedback to track insects mid-flight, adjusting optical focus faster than the human eye could. Lightweight, solar-powered GPS trackers allow birds to be followed over seasons without recapture. Computer vision systems, mounted in fields or inside hives, distinguish between species, behaviors, and individuals. The collected data is multidimensional, continuous, high-resolution behavior maps. But these systems come with their own set of challenges. First is size and power. A device small enough to ride on a bee or a songbird still needs to process complex data, often without a reliable power source. Battery life, solar charging, and weight constraints limit duration and functionality. Then there's the problem of real-world environments. Outdoor light shifts constantly. Wind shakes cameras. Backgrounds change. AI models trained in labs can struggle to recognize animals in the field, and reliable data transmission, especially from oceans or remote locations, remains a technical barrier. Solving these challenges requires efforts from multiple aspects. Starts with design collaboration. Biologists define what to study. Engineers build the machines. AI researchers train the systems to extract useful behavior. No one team can do it alone. From an engineering standpoint, field reliability and power longevity are serious challenges for almost all unmanned systems. They break, drain batteries, and struggle with unpredictable environments. Only steady progress across hardware, software, and sensing will push these systems forward. To move faster, researchers also need to actively search for commercialization opportunities. If some of these tools find real-world applications, like crop monitoring or conservation, it opens the door to funding, scalability, and can attract industry talent. That's how the research field will grow sustainably. Looking ahead, the future lies in scale and coordination. We're moving toward networks of devices, like drone swarms and floating sensors, that can monitor entire populations, not just individuals. These systems will need to get better at collaborating and adapting to new environments. At the same time, we need to ensure that they remain lightweight, energy efficient, and non-invasive. The goal is always to observe without interfering. Now that you've made it to the end, here are the key takeaways we want to leave you with. AI-powered robots are essential for wildlife monitoring, offering active tracking and long-term, multidimensional data collection. Field reliability remains the biggest barrier to widespread deployment. Future progress depends on strong cross-disciplinary collaboration and exploring commercialization opportunities. Key citations that contributed to the production of this video are listed in the description section.